So, hello everyone, welcome to the tutorial 6 of Introduction to Classical Mechanics course. Today we will do some problems regarding the central force. Okay, so let us start. So in the previous day I have already shown you that you can write the equation of a particle moving in the central force field in this way: d2u d phi square plus u is equals to minus m by l square u square f of 1 by u, where we have assumed that u is actually 1 by r. Now this is a very important result. I will show some application of this result today, but before that I will derive this result using another method. I mean, from the total energy I will derive this exact same result. Okay, so as we have taken u is equals to 1 by r, that means your r dot, which is dr by dt, that is du d phi dt, right? If you calculate it, then you will get minus 1 by u square du yes, minus 1 by u square oh sorry, there was a mistake. So yes, so r dot is equals to dr dt. Okay, so we can write it as dr du d phi and d phi dt. Okay, then if we calculate it, then your dr du, that will come as 1 by u square du d phi and phi dot, because d phi dt is actually phi dot. So it is actually your l by m du d phi, because you already know that m r square phi dot is equals to l. So if you put this equation in this expression, you will get this. Okay, now the total energy of a particle moving in a central force field, that is half m r dot square r square phi dot square, it is the kinetic energy plus the potential energy, that is Vr. Okay, so now we will substitute the r dot, this r dot, by this r dot, which we have got that minus l by m du d phi. So if you substitute, we will get as minus l by m du d phi whole square plus r square, and phi dot, in phi dot we will replace this, that l by m r square, that means l by m r square. Okay, and that potential energy as it is. So if you calculate this, you will get the final result as l square by 2m du d phi whole square plus u square plus v r. Okay, now this is your total energy, and here one thing you can see that I have written it in some terms are in u and some are in r, and always remember that r is actually 1 by u. Okay, so this is your total energy expression. So it is also a very important result for your central force. So while doing central force problem, if you can remember some result, then it will be very useful for your application. So please try to remember this particular result. When a particle is moving in a central force field with a angular momentum capital L, then the total energy can be expressed like this. Okay, so yeah, now you also know that the central force is I mean, it is conservative, and that's why the total energy in a central force field is always constant. That means dE by dr equals to 0. Now if you use this condition, and in place of E you write this expression which we have got, then that will come out like, I am directly writing the result, but you just derive it, it is very trivial. D phi du du dr plus 2u du dr. This is very easy, just do it, and I have used the chain rules multiple times, that's why it is looking like this complex, but there is no complexity in the expression. So it will give you L square by 2m 2 d2u d phi square minus of u square, because this du dr will give you a minus of u square plus 2u and again minus of u square. Okay, so this is the expression of, I mean, if you use the condition that your E is constant. Okay, now now let me see what I have okay, yes, so this is also an important result you should remember. Now the actually what I have already done, this equation, this is the equation of the particle, equation of motion of the particle. Okay, now we can write this f1 by u, I mean f1 by u in terms of this left hand side. I mean we will take only f1 by u in the right hand side, and all the other value or the other expressions or all the other variables we will take it to the left hand side. Okay, then we will get fr is minus L square u square by m times what was in the left hand side. Okay, so this is the force, it is same as 1 by u. So 1 by u, which is equivalent to f of 1 by u, which is equivalent to f of r, which is the force, that can be expressed in this way. Now suppose you are given a particular form of orbit, that means u is given like this. Suppose you have been given this your particle is moving in this orbit in the central force field, and you have asked to calculate the force which is acting on the particle. So we can do it by using this particular equation. So that's why I asked to remember this particular equation, which is very important for central force field. Okay, now we will do that. So your u is given as 1 by a 1 plus cos phi. Now what we need d2u d phi square. Okay, so du d phi is sin pi by a 1 plus cos phi square. Okay, and your d2u d phi square, this is an example, you can think it as an example. Okay, your u is given, I mean r is given, and we are trying to find out the what is the force acting on the particle. So cos phi square plus 2 sin square phi by a is a UV method of differentiation. Okay, so it will keep. So your d2u d phi square is this, and your du d phi is this. Now our equation tells that du d phi square plus u, that is actually our force which is acting on the particle. Okay, now it is now a very trivial job, that is cos phi a 1 plus cos phi square plus phi a plus cos phi cube plus u is already given as your in the equation, or that is 1 by a cos phi, 1 by a 1 plus cos phi. Okay, so this is your force f of r. Instead of r you can write u also, that doesn't matter. Okay, so if you calculate this expression, your fr will be cos, the denominator will be a 1 plus cos phi cube, so cos phi into 1 plus cos phi plus 2 sine square phi plus 1 plus cos phi whole square. Now just write it in a open form. I mean 1 plus cos phi whole square, you just write it in 1 plus cos square phi plus 2 cos phi and do the multiplication operation in the first term, then you will get a form like this square. Okay, so now if your fr is 3 by a cos phi square, and it is already given that u equals to 1 by a cos phi, that means you can write it in this way also. Okay, so hence your fr is equals to this 3a by r square. So you can say that when a particle is moving in a force in a orbit which have this expression, so that particle is being acted upon by a force which has a form of 3a by r to the r square. So it is the force acting on the particle. So by this method you can calculate what is the force acting on the particle if you are given any arbitrary form of the the path of the form of the path which is the particle following. So this is a method of doing that. Okay, now from this one thing we can do that this particular form, which is the path of the particle, if we draw it, it will look like this. Okay, so it will look like this, where this is the center of the particle and the force is acting along this r. This is the phi. Okay, so this is actually the form of the orbit which is the particle is following. Okay, and it is in the polar coordinate. Okay, so it is a way of evaluating the force on the particle. Now we will go to another problem. So please try to remember this particular expression, which is very important, E for E, and also the equation of motion which we used to derive. Where is it? Yeah, this one. These two equations are very important. Please try to remember if you want to do problems very easily. Otherwise you have to derive it. You can derive, but it will be, time saving if you can remember this. Okay. Now as one thing sir already has taught that if a particle is following a elliptical orbit under a central force field, then we can express the particle's orbit as this: L by r0 1 plus e cos phi. Okay, where L is the semi-lachaise rectum of that particular ellipse, which can be expressed. I should write this in red because these are important. These small things you should remember always. So L square, where L is the semi-lachaise rectum, small l, and capital L is and capital L is the angular momentum. So L can be expressed in this way. Also eccentricity, which can be written in this form. So these expressions are very much useful when you are in an exam. So in dealing those exam questions, this is important. You should remember all this, and if you express it in one thing I have, this is capital L square, okay, the angular momentum, and if you want to write it in a form of semi-lachaise rectum, then it will be 2EL by K. So all these things are important. It is for a ellipse which has a semi-major axis of A and semi-minor axis of B. and eccentricity of epsilon, and those a and b are also related. Let me find it, I have also forgotten. Yeah, so you can write your a as L upon 1 minus epsilon square, and B is actually A times 1 minus epsilon square, and if you put the expression of A, that will give you L upon 1 minus epsilon square. So all this semi-Laplace rectum, this eccentricity, this semi-major axis and semi-minor axis, all the expressions are important, because repeatedly you will substitute some variables into other variables while dealing with the problem. So if you can remember these equations, I mean expressions, it will be very much useful, because several times we will do conversion between eccentricity and semi-major axis or semi-minor axis. So this will come repeatedly in your problems. Okay, so please try to remember all these things. These are not so, I mean, complex to remember. Okay. Now, using all these things, we will deal with some problems. Like one thing we will do, that is called nature of orbits. It is a particular problem. Okay, and problem. Okay, now everyone knows that what is the escape velocity. So escape velocity is that velocity, if we give that I mean if we throw a particle with that velocity, then it will not come back to that position from where it has been thrown. So that is called the escape velocity. Now we will use the I will do a problem using that definition. Okay, so consider a particle that is moving under a central force, and the total energy can be written as E, and for any time E is a constant, or I mean any place E is constant. So if you write half, it is at R. Okay, now suppose you are throwing the particle from a particular position R with escape velocity VE. Okay, so it will go to infinity, where I mean that is the definition of escape velocity. So it will go to the infinity, and that particle will have no potential energy as well as kinetic energy. So it is the condition of escape velocity. I am writing as EV, where VE is the escape velocity. Okay, now from these two equation, just replace this VR by this by the second equation, which will give you VR as minus half m VE square. So that will give you half m V square minus VE square is equals to E. Okay, so from these two equation you will get it very easily. Now what we will do, that our eccentricity of the particle which has been thrown, it is 1 plus, that's why I asked you to remember all these things. Now we will use this particular expression, where eccentricity square is actually 1 plus 2e capital L square by mk. Okay, sorry, yeah, mk square, this one, mk square. Now if we replaced this e by this e, then we will get it as 1 plus L square by k square v square minus v square. Okay, so this we will get. Now let us draw the picture. So suppose it is the earth or whatever. Now we are throwing the particle from this position in this direction, okay, which is making an angle alpha, and yeah, alpha, and it is the velocity v. Okay, so note that I am not writing is VE, so I am not in this picture I am not telling that I am throwing the particle with escape velocity, just I am throwing the particle with v. It is not escape velocity. Okay, so we will calculate, I mean, how v is related with the escape velocity or other things. Okay, so for this particle, your L, that is the angular momentum, so let us call it is the origin O and this distance is r0. Okay, so with respect to O, the origin, the angular momentum will be r0 cross p. Okay. And we are concentrating, I mean focusing on the value of the angular momentum, not the direction. That's why I have written L without the vector sign. Okay, so if we do it, it will give us, as we are throwing with the velocity v and suppose the particle mass is m, that means m v r0 sine alpha. Okay, because the angle between momentum or the velocity and the position is alpha. Okay, so this L again we will substitute in the eccentricity. So L square was m square v square r0 square sine square alpha by k square, and there is, yes, v square minus v square. Okay, so the point is the escape velocity of the particle at this particular position is v, no doubt in that, but we are not throwing it with ve, we are throwing it with the velocity v only. Okay, and as it is in the, and we are assuming that it is in the inverse square law field, that's why your v at the position r0 is like this, minus k by r0. Okay, and if we use this condition for the escape velocity, that half mv square plus vr equals to 0 at this particular position r0, that will give us what should be the escape velocity at that particular position. So your vr is minus k r0 is equal to 0. It is at r equals to r0. Okay, so your half m v square can be written as minus plus, it is k by r0. Okay, so this we need in our calculation, I mean the expression of epsilon, which is the eccentricity, the expression of the escape velocity at that particular position r0. Now, okay, so next we will do one substitution in this particular problem. So in this epsilon square, or it is not square because I have given that root over sign, so sorry for that, it is epsilon, not epsilon square. So in this epsilon we will substitute value that is c. C is actually v by ve. Okay, so that is the ratio of the velocity with which I have thrown the particle and the escape velocity at that particular position. So if you use this particular expression c, not expression, the value c, then your epsilon can be written as this. So I have substituted the c in terms of v by vc, and I have substituted this k by r0. Yes, and I have substituted my escape velocity in terms of that k by r0. So if you do it, you will get this expression. Just try to do it by yourself, it is not a hard thing. So this is now a very interesting equation. Okay, why? Because you know that for a circular orbit, epsilon is equals to 0. Okay, now if we write epsilon equals to 0, that means yes, 1 minus 4 c square 1 minus c square sine square alpha is equals to 0. Okay, now we will do some manipulation, that is 1 plus 4 c square minus 1, I have taken 1 common, sine square alpha equals to 0. Now from this 4c to the power 4 sine square alpha minus 4 c square sine square alpha equals to 0. Let me check. Yes, yes, okay. Now okay. Now if you do some trigonometric manipulation here, so that will give you 1 by 2 c square sine square alpha by alpha square is equals to 4 c to the power 4 sine square alpha minus 1 times sine square alpha. Okay, so yes, let me check. 1 plus sine square alpha 1 minus, that is 4 c to the power 4 sine square alpha. Yes, yes, so this is correct. That is some trigonometric manipulation, and if you write 1 in terms of sine square cos square, then if you again substitute, then you will get this. I have not done it by myself, but I will ask you to do it, and if you don't get this particular line from this line, then let me know. I will do it explicitly on the next day. But there is a point why I am writing this simple equation in terms of this complex, I mean in this complex way. So the point is the following. Just a second. 3933. Yes, okay. Now one thing you can see, that left hand side of this particular equation, that is this one, so this left hand side is non-negative because it is a square, right? It is, the left hand side is always positive, this part. But this right hand side, there is I mean, if your alpha is less than pi by 2, that means sine alpha is less than 1, then the value in this parenthesis, it will give you a negative sign. Okay, and also this, I mean the whole sign, that cumulative sign of this right hand side will be a negative. So this, then this equation is not valid, because your left hand side is positive, and if your alpha is less than pi by 2, you are getting a negative sign in the right hand side, so that is not valid. So it is only this equation is only valid when your alpha is pi by 2. That means your this term in the bracket, that will be 0, and your right hand side will give 0 for pi by 2. So 0 can be accepted in the right hand side, because some square, 0 can be a square, but negative cannot be a square. So this is the constant of this particular equation, that your alpha should be always pi by 2 for this particular expression, and so your value of alpha is pi by 2, and your c is v by ve, which is 1 by root 2. Okay, because if you put alpha 0 here, then from this right hand side equation, I mean 1 minus 2 c square sine square alpha square, that will be 0, and from this equation you will get that your c is equals to 1 by root 2, which was the v by ve. So what is meant by this particular, I mean analysis? That is, so from this particular position, from where you have thrown the particle, if you throw the particle with a velocity which is 1 by root 2 times of the escape velocity, and at a radius pi by 2, so your throwing angle is pi by 2, this alpha is pi by 2, then you will get a orbit which has a eccentricity is 0, and that means that orbit is circle. Okay, so to get a circular path for this thrown particle, you have to throw it at an angle of pi by 2 with a velocity of ve by root 2, where ve is the escape velocity. So that is the important point. And by the same analogy, when it is following, let me see, I have also forgotten that, yes. So when you use this condition, epsilon is greater than 1, then you will reach to some other expression that this must be the angle and that must be the value of velocity which with which it should be thrown to get a hyperbolic orbit. So by using various values of epsilon, you can get the various condition which should satisfy to get a particular orbit. Okay, now okay, so this is I will write something, just try to do it. So if your velocity is greater than escape velocity, and yes, so and if you throw it at any angle, that will follow at a hyperbolic path. Second, if you throw it at v equals to ve, okay, that is the escape velocity, that will follow a parabolic path. So it will follow different path depending on the, I mean, all these are coming from the condition of epsilon, that is the eccentricity. And if you throw it by a velocity this, that means this was the corresponding to a circle, this was corresponding to escape velocity, that will give you a elliptical orbit. Okay, and that particular thing what we have done, that v is equals to v by root 2 and angle is equals to pi by 2 for this particular condition, it is circle. So you can see that the angle is coming into the picture only when we need to get a circular orbit. Okay, that is alpha equals to pi by 2. And if you throw it at a velocity less than v by root 2 but greater than 0, of course, that will also give you a elliptical orbit. Okay, so it is this particular thing, it is called a bound state. And it is the equation which which is used for ballistic missile, or ballistic missile, you know that it will follow a trajectory which is ellipse. So it is the equation which has been used for this particular thing, it is called the bound state. Now these are important. If you want, you can derive it by yourself also, similar way which I have been shown. I have just done this particular thing, it has been done, and all the others you can do it. Okay, so try to do it. Okay, now any problem till now? Okay, okay, now we will do a very small estimate of escape velocity. Okay, so remember the equation of escape velocity, this one, half mv square plus vr equals to 0. So equation of ev is half mv square plus vr equals to 0. Now suppose we are at earth. So for earth, our gravitational field is actually g/mm by r, right? Because our force is like and I am only writing the value, I mean modulus value, so g/mm by r. Now if you use this, so I am trying to find out what is the escape velocity of a particle which is thrown from the earth. Okay, so your half mv square is equals to g/mm by r. This m will cancel out, where capital M is the mass of earth and small m is the mass of the particle. That much you know, I think. Yes. So your v escape will be 2 gm by r. Okay, this is 2 gm by r. Now I will use a particular formula that is coming from the gravitational chapter, and you have done it in class 12 or anything, I think. So you can write your gm as small g r square, where small g is the, I mean, acceleration due to gravity. So you can write this, just try to find it or try to recall it. It all has already been done. Okay, so g r square by r, and you will get 2 gr, and this is also very familiar to you, I think, that v escape at earth surface is root over 2 gr. This is like, we know always, and we have done various problems with this particular expression. So if we put our values, that suppose r roughly take at is 6400 kilometer, and g is 10 meter per second. So if you include all those values, you will get a escape velocity which is in kilometer per second, and you can convert it in kilometer per second. So that will give you a just 8 root 2 kilometer per second, which is roughly 11.2 kilometer per second. This is also, I think you know the value roughly. So this is the value of the escape velocity for a particle that has been thrown from the surface of the earth. So if you throw it at a velocity more than this 11.2, it will not come back to that point from where it has been thrown. So that's why it is the escape velocity. Okay. Okay, now I am again asking you to remember all these formulas which are very important, and I will add one more formula in this. So it will be very beneficial if you can remember. Okay, that's why I am saying again and again. Okay, so when a particle is in a circular orbit, okay, so okay, then if it is moving in a circular orbit, then the centripetal force will equal to the gravitational force. That's why it is stable in that particular circle. So we can write that the force which is acting inward is actually the force which is acting outward on the particle. Okay, so this is always true. I mean, a particle which is moving in a circular orbit, so this is the force which is acting outside, that is mv square by r, and this is the force which is acting inward. So k may be g capital M small m. If it is gravitational force, then it will be g m small m by r square, if the mass is capital M and this mass is small m. Okay, so k, this is the value of k. K can be anything. So if it is electrostatic potential, then the k will be q1 q2 by r square, where q1 q2 are the charges of those two particles. Okay, so that's why let us for this time, for now, let us consider k as a general quantity, not gmm. Okay, so this equation follows. Then what is the total energy of the particle? That is, as always, mv square, the kinetic energy plus potential energy, and you know that you can write it, I mean, from this equation you can write v in terms of r and k, and that will be your k by 2r, and our potential for this particular force field is minus k by r. So our total energy is minus k by 2r. Okay, I should change that. Yeah, so this is same as sir has already shown, that if it is a elliptical orbit, it is minus k by 2a, where a is the semi major axis, but for circle it is minus k by 2r, where r is the radius. Here there is no difference between semi major axis or semi minor axis, because both are same. Eccentricity is 0. Okay, so that's why it is the, I mean, analogy. Analogically this is correct, that it is for ellipse and this is for circle. Now we will calculate the angular momentum of this particle. Right? So angular momentum is always r cross mv. Okay, and we are interested in the value only, so that is rmv. You can say r is the distance. So if you again put your v in terms of k, r and m from this particular equation, then you will get it as okay, so r m and v will be k r by m, I think k r by m, or just let me check, k by r square, k by r is equals to mv square by mv square from that equation, first equation. So v square is equals to k by r m. Yes, so your v will be k by m r root over. Now if you do it, you will get k m r. Okay, so this is also an important result which you should remember, then you can do. I mean, here I have written 1 2 3 4 and just add this particular expression in this list, so let us call it as 5. So please try to remember this expression. These are very useful while dealing with the problem. So if a particle is moving in a circular orbit, and you should also remember the condition also, it is not valid in an elliptical orbit. So if it is moving in a circular orbit with a potential, with the force which is following by k by r square, or the potential which is following k by r law, and have a mass m, then the particle has a angular momentum of root over mkr. Okay. These are very important expressions. Just try to remember that. You can calculate this L from your first principle, no problem in that, but if you can remember, then it will be very helpful. That's what I want to say. I am not saying that you cannot do it, you cannot derive it. Always you can derive it from first principle. Okay. Now another interesting thing, I mean, I think it is interesting, I don't know what you will think. So we will do something. So what should I give a name? Okay, now we will do a problem, I mean example, which will give you some more interesting result. That let us just consider a particle fr which is moving like minus k by r square, same as previous case, but here I am not saying that it is moving in a circular orbit. It can follow anything depending on the eccentricity. Okay, so for this particular force law, I will try to calculate the velocity of the particle. Okay, but that will, I mean, you can calculate velocity by the equation of motions or the energy conservations also, but here I will do it in a different way, and that will give you another interesting result that is very useful for the problems. Okay. Okay, so let us now do. So for a particular conic section, you know that our equation is 1 plus epsilon cos phi minus phi 0. If phi 0 is equals to 0, then you can write it 1 plus cos phi also, no problem in that, but I am taking phi 0 here. So L by R is 1 plus epsilon cos phi, and epsilon is the eccentricity, small l is the semi-lattice term. It is the, I mean, you should always remember that it is the it is the important thing. This you cannot forget. You can forget all the other thing I have told you, but this you cannot forget. L by R is equals to 1 plus E cos phi. Always remember that. And your small l is capital L square by mk. You see, it is again useful for this particular problem. So try to remember. Now R is 1 by U. And your u is 1 plus epsilon cos phi minus phi 0 divided by L. Yes. Yes. Okay. Now r dot is minus, should I write it again, dr du d phi dt. That means minus 1 by u square du d phi dot, and if you do all the things, it is same as before, L by m du d phi. And one thing I must tell you that here I have considered the typical case of, I mean, solar system like systems where the central mass is very massive. That's why I am just writing small m, which is an approximation. And if you are doing a two body problem, just replace your small m with mu, and the result will be same. There will be no change. Where your mu 1 by mu is equals to 1 by m1 plus 1 by m2. So yeah, now your velocity v square is r dot square plus r square phi dot square. Okay. Now r dot, which I have already calculated, plus r square, and your L is equals to m r square phi dot. Always remember that. From here we will write it in this way. These are all manipulation of expressions, I mean, and by this manipulation you are getting some interesting results which are useful. Okay, so if you do it, your velocity, I am writing it directly, L square by m square du d phi square plus u. So it will be your velocity. Now the interesting thing is, if you substitute your u, which has been written here, 1 plus e cos phi by phi 0 phi minus phi 0 by l. So if you substitute it properly, just substitute it, there is nothing in that, then you will get it as k by m 2r minus 1 minus epsilon square by l. Okay. Yes. So it is just a matter of substitution, you can get it. So your v square is like this. So again I am emphasizing and adding this expression in the list, which you should remember, that a particle which is moving under a force k by r square and have a eccentricity e, if you know all those variable, I mean all those parameters, then you can write the velocity in this form. And this is very important while dealing with the problems. Sometimes it can reduce your difficulty of dealing problems, and depending on the value of I mean ellipse. So here I mean, yes, so here one thing we have assumed that for this expression, I mean, I have not done it. So while you will do it, you have to substitute your relation between your L and epsilon. So if you take L as 1 minus epsilon square, which is valid for an elliptical orbit, because here I have considered the general orbit, and if you write it L m is epsilon square minus 1, which is valid for a hyperbolic orbit, because you know that for your hyperbolic orbit epsilon is greater than 1, and for your elliptical orbit epsilon is less than 1. Just let me check. Yes. So if you substitute it in 1 minus epsilon square or epsilon square minus 1, you will get a sign difference here. I mean, for the 1 minus epsilon square for the elliptical orbit, you will get a minus sign, and for a hyperbolic orbit you will get a plus sign. Okay, so depending on the value of epsilon, and in that case your epsilon 1 minus, because your 1 minus epsilon square, I mean, it is determining what will be the value of the sign just previous to it. So depending on that, you will get the value minus or plus, and it is valid for whether it is elliptical orbit or it is hyperbolic orbit or it is a I mean circular orbit. For circular orbit, your both r is actually a, or a is actually r, whatever you can say in this way, where r is the radius and a is the semi-major axis. So by substituting this, you can also get the expression for the velocity for a circle also. So this is a general thing which will give you ellipse, hyperbola or circle. So try to remember this particular expression also, it is very important. Okay, and if we write it in a or more compact way, then it will give you 2 by r plus minus, or I should do minus plus 1 by a. Okay, so this minus plus sign is coming to this, I mean whether you are putting 1 minus fc square by 1. Okay, okay, so there is a silly mistake, I mean problem of concept, I should correct it. So it will be minus, there will be no plus here. When you will put your L by, I mean 1 minus epsilon square in terms of L by A, then that minus and plus sign will occur. So that is my mistake, very sorry for that, that is my bad. So minus and plus will come in this particular expression. Okay, when you are substituting your 1 by 1 minus epsilon square by A and L. So this is the important result. You can remember any of these two, no problem. It is much more just k by m, where k is your, I mean method of remembering is just k is your the constant with the force or potential, k by m, m is the mass of the particle, in the parenthesis it is 2 by r plus 1 by a, where r is the distance and a is the semi-major axis. Okay, so you will get it. And I will ask you to calculate the velocity by substituting r is equals to a from this expression, and you will get exactly the same expression which have been done here. The v square will be same as before. So try to get the v square expression from these two, I mean from this and this, and show that they are same. Okay, okay, this we have covered. Now one small thing I will do at the last, that is the Kepler's law. So Kepler's law of periods. Time period. Okay, okay, so one thing I need for this, yes, L by m, yeah, t. So if a particle which is following this particular path, then the then the time period, it has been already shown in the first class that s is no, t is the time period, and L by 2m, just a second, yeah. So s is the area of the orbit. If s is the area of the orbit, then it can be expressed by this. This has been already shown, just check it. Okay, s is the area of this orbit. Okay, now yes, t m, yes. So for a ellipse, the area is pi ab, that is L by 2m t. So where t is the time period. Okay, and L and m, you know that capital L is the angular momentum, m is the mass. So if you write it, it will be 2 pi m ab by capital L. Okay, now again that expression which I asked you to remember, those are very important, very important. Just this one, that b is a times root over 1 minus epsilon square. I will use this expression here. So b is a times 1 minus epsilon square root over. So if you use this, you will get a square minus 1 minus epsilon square. Okay, so 2 pi m by L square and 1 minus epsilon square. Okay, so let us go to the second expression. I think, yeah, this one, a is L by 1 minus epsilon square. That means root over of 1 minus epsilon square is root over L by a. You see why these are so important. So that we will use here. It is root over L by a. Okay, and small l is equals to L square by mk. So using that also, just substitute that 2 pi m by L square by mk a. Okay, then you will get 2 pi a to the power 3 by 2 m by k to the power half. So this is the time period of a particle with mass m and acting force is k by r square. So this, and a is the semi-major axis of that ellipse, which is the orbit of that particle. So it is the time period. Now let us concentrate on the forms of k. Okay, so so if now suppose the earth is moving around the sun, or if the earth is moving around the sun, then this mass of the m is the earth mass. So and thus k is the gravitational force, that is gmm by r square. I mean k is gmm. So if it is gravitational force, that is gmm by r square, and your k is actually gmm. Okay, now let us consider that instead of earth mass system, just two mass m1 and m2, they are comparable. Just I will then replace the m as mu. So your, I mean, there is no harm if you consider earth sun system and keep it as capital M also, but just let us use mu for this particular case. So mu by k, and your mu by k would be, so mu would be m1 m2 by m1 plus m2 by g m1 m2. So it will be good to tell it as small m and capital M, I think. Not I have, then I don't have to write m1 m2 everything. So it will be m plus m and g m. Okay, that will give you capital G m plus m. Now if your, this is for a general mass where I have not considered that capital M is very greater than small m till this point, but you can consider it, there is no problem. So if you consider that, okay, let us first write without considering it. What is 3 by 2 m by k, k is mu by k, yes, so mu by t, yeah, t is to the power 3 by 2 m by, oh, that is mu by k, that's m plus m to the power half. Okay, this one. Now suppose m is very greater than m, small m, then it will be 2 pi a cube, and I am squaring both sides, 1 by, if capital M is small, very greater than small m, then this can be written as capital M only. Okay, oh, this will not be 4 pi, this is 4 pi square. So your t square will be like this. Now yes, now suppose here is the sun, it is the earth, it is Jupiter, just suppose. Okay, so the expression of the time period don't have the mass of earth and Jupiter, because they are very small compared to the sun, and it has the mass of sun only, that is capital M. So this is constant, this g is constant, 4 pi is always constant. So your t square is varying as a cube, where a is the semi major axis. That means this is the distance for, let us write ae for earth, and this is the distance for aj, that is Jupiter. So if you want to calculate the time period of these two planets, it is related like this. Okay, so you can be given some problem like it has been told that your suppose Jupiter has a semi major axis of this much, and it has a time period of this much, and Earth has a semi major axis of this. So your aj, ae and tj are given, and you can calculate your t very easily from this particular expression. And this type of small problems generally comes in the exam, which carry very small marks, but it is important. And so by this formula you can calculate, it is only depending on the semi major axis of the particle, the time period. Okay, so the condition, but there is some condition that you should always remember, that for this condition capital M is very greater than small m. That's why we can neglect the mass of the Earth and Jupiter. Otherwise, if it is similar, comparable to sun mass, then mass of sun, solar mass, then we cannot eliminate. We cannot eliminate that small m from this expression. Only it is true when a very massive object is sitting at the center, and very less mass compared to that massive object is revolving around itself. So that's in that case you can get this type of expression. Okay, so this is called the Kepler's third law, or the law of orbit. I think it is third, yes. Okay, so in that list in that list, that 6 expression, just add this expression also, t square is a cube. Okay, so again I am telling you this 1 2 3 4. Okay, I cannot do it here. So this L, this epsilon, A and B in terms of L and epsilon. This you can also remember, but this is important, which I have done. And this one, total energy of a particle in a circular orbit, and the angular momentum in terms of its mass and the radial distance from the center. This expression of the velocity in terms of radius and the distance and the semi major axis and mass. So, and this particular thing, orbit, time period of a orbit of a particular mass revolving around a higher mass, is very much important. So please try to remember all this, and you will see that all this expression will help you while you are solving some problems. Okay, so I am done for the day, and if you have any question you can ask, and if you have any question later also you can email me, so no problem in that. So my email ID is this. You can send me a mail here also. Okay, then we will meet next week, and for the day we can end the meeting. So goodbye.